be speaking on new directions in anonymization, permutation paradigm, verifiability by subjects and intruders, transparency for users.
Thank you. Hope this works. It's really intimidating to be in a room with pictures like that, but I hope will be. Well, the challenge I'm going to talk about is a different one from the ones that have been discussed so far. It is about empowering subjects and also users in the anonymization process. And this is joint work with Krishnamurty Muralidhar from University of Oklahoma. Well, this is more or less the outline. I will discuss first this permutation model of microdata masking, and then I will proceed to deal with subject verifiability, and also with some intruder models and etc. So maybe it's better to go, and otherwise the outline may be too intimidating. Well, this is the motivation for this talk. Especially in big data collection, but also elsewhere, there is a crowd of controllers collecting data. So it cannot be assumed that subjects and users trust a particular controller, or let alone all of them. So there is a challenge. This is for Natalie, this challenge. There is a pressing need for anonymization by the data controller to be verifiable by subjects and transparent to users as much as possible, at least. Of course, if in the specific case where data are explicitly collected from subjects, so that they are aware and are providing the data themselves and they are aware of providing the data, then there are alternatives. One possibility is local anonymization, which has been discussed already in the literature, and another option is this collaborative anonymization that I hope to briefly discuss here. There is in the case of, I will focus mostly about creating public microdata files or safe microdata files. So in this case, there is a further complication to the verifiability and transparency, which is the diversity of principles that inspire anonymization. So there is swapping, there is noise addition, there are several ways to anonymize. And then this diversity makes it difficult on the one side to select the best method, and once you have the method, to select the best parameters to achieve an optimum trade-off between utility preservation and disclosure protection. So let's start with this idea of this permutation model. So this is a very simple thing, and maybe the pseudocode doesn't help, but I hope. Well, the idea is, and I will elaborate, I will build on this. So let's consider an original attribute with n values, and let's consider there is also an anonymized version of this attribute, and we call it y. So original attribute x with n values x, or anonymized attribute y with n values y, y1 to yn. Then let's compute the rank of the anonymized values, so order them and the rank, and let's let the rank of the ith y value be j, and then take as zi the original value with rank j, okay, and then release these values z instead. Well, return these values. That's the thing. So from an original data set and an anonymous data set, you derive this z data set. Of course, we are here considering a single attribute to make things simpler. Now, if there are several attributes in an original data set x and anonymized data set y, we can repeat this procedure independently for each attribute. It turns out that this attribute z that you get here is actually a permutation of the original values. Okay? So we call this attribute a reverse mapped attribute z, which is a permutation of the corresponding original attribute x. Then the rank order of z is the same as the rank order of the anonymized attribute. So the values are the same as in the original attribute, and the rank order is the same as in the anonymized attribute. And then if we look at this reverse mapped z, we can imagine that any microdata anonymization technique is functionally equivalent. It is equivalent to first permuting the original attribute into Z, and then adding some noise to turn Z into Y. But the noise we add is very small, because the ranks of Z and Y are the same by construction. So the noise is quite small. Then we have that the basic component of anonymization is permutation, except for some small noise addition. So this is why I call this the permutation model, because in that way we can view anonymization as basically a permutation. Then we can construct, we can state a privacy model that is subject verifiable, which I call DVF permuted privacy, as follows. So we have a vector of the negative integers, which are distances actually, rank distances, okay? Then we have a vector of non-negative real numbers, which are diversity measures for attributes. We have an original data set X and an anonymized data set Y, both with M attributes. And we have a record level mapping that maps records in the original data set to records in the anonymized data set. Then we say that this anonymized data set satisfies this DVF permuted privacy with respect to original record, to a certain original record in the original data set. If when we consider the values Y star of the jth attribute, jth anonymized attribute, closest to the corresponding value of the jth attribute in this original record, then it turns out that the anonymized record corresponding to this original record satisfies that the rank difference between the ith value of the anonymized record of the jth attribute, well, the jth attribute in the anonymized record has a rank that differs at least dj from the rank of the most similar value to the jth original value here. And then this dj is called the permutation distance for the jth attribute. So in a way, the greater this distance, the largest is the longest is the movement, the rank movement of the values of each jth attribute. And then what is the role of the other parameter, this diversity vector? Well, if this data set is the set of values of the sorted jth anonymized attribute whose rank differs no more than dj from the rank of the most similar anonymized value to the original value, then the diversity of this data set is greater than the jth component of the diversity vector, according to some diversity criterion. So let's explain a little bit the definition. So if we if the anonymization is just permutation without anything else, like rank swapping or whatever, then the most similar anonymized values to the original values are exactly the original values, because then you just have a permutation of original values in the anonymized data set. Then another explanation is that for each original record, the data protection can take as the corresponding anonymized record, well, as fx, sorry, the anonymized record that derives from x according to the method, assuming that this can be traced. I will discuss later in the case of synthetic data or other situations in which it may not be obvious which is the record that derives from x. Now, the subject can take, in this case, if it is not obvious, the subject can take as a possible approximation for f of x, the record in y whose attribute values have the smallest rank difference with the most similar values in the anonymized data set, one independently for each attribute, to the original record. And then the diversity criterion or diversity criteria in this diversity vector can be the variance or one of the criteria used in L diversity or the criterion used in T closeness. There are several possibilities to define diversity. Now, if we have DVF permuted privacy holding for all records, all original records in the original data set, then we say it holds for the entire original data set. Then how can we compute the vector of permutation distances given an original record corresponding to a subject? Well, here we have an original record, and we have the anonymized data set that contains n records with m attributes each. Now, as before, define for each attribute the anonymized value in this jth anonymized attribute closest to the original value of the jth attribute. Then sort this jth attribute, sort the anonymized data set by the jth anonymized attribute, and let the rank of this y star j be denoted as this, okay? And then also compute the ranks of the jth attribute in the anonymized data set. Now, if the anonymized record corresponding to the original record is this yp1 to ypm, we can compute this distance vector by taking as the jth component of the vector the rank difference between the jth component of this anonymized record corresponding to the original record and the rank of the most similar value in the anonymized data set most similar to the original jth value in the original record. And then this yields the distance vector for a certain original data set given an anonymized data set. And this can be checked not only by the data controller but also by the subject, as we will see. Now, this verifiability, as I said, these parameters can be checked by the data predictor and also by the subject, because the subject can use the anonymized data set, which is assumed to be published, and her original record to compute these most similar values in the anonymized data set to her original values in her original record, and then get the distance vector with the previous algorithm. And then the subject can also check the diversity condition on the anonymized data set. Hence, the subject can make sure the values in her record have been sufficiently protected in the anonymized data set, understanding by protection permutation of values, and that there is enough diversity. So the underlying notion is that if you manage to split the values of in the original record into enough distant records in the anonymized data set, then you are protecting the user, because what is confidential is the correlation between the various attributes of the user in the original record. If this correlation is no longer there, then the confidentiality is protected. We assume that the marginal value of each attribute is not that confidential, that the confidential thing is the connection between the values of the different attributes in the original record. So this is as much as I wanted to say for verifiability of this permutation and diversity. Then let's turn to the adversarial model, which is another issue that I wanted to tackle. This paper is, as the title says, is mostly new direction. So I start things, I'm not finishing them. But if anyone is interested, I would be very happy to discuss. So let's now discuss something about the type of intruders that we can consider in the anonymization process. And let's draw some inspiration from cryptography, which is something that is often done. In cryptography, you have the ciphertext only adversary, which is an adversary that has access only to ciphertext. This is the most innocent type of adversary in cryptography. In anonymization, this would be equivalent to an adversary that has only knowledge of the anonymized data set. Then we have the next adversary in severity, in seriousness, is a known plaintext adversary, which in cryptography means this means that the adversary has access to pairs of plaintext ciphertext. In our case, in anonymization, it means that the adversary has access to pairs of original and anonymized records. We can also go further and assume that a more powerful adversary, in this case the chosen plaintext adversary, This would be an adversary that can choose a plain text and get the corresponding ciphertext. In our case, an adversary that can choose an original record and get the corresponding anonymized record. And then we can also think of a chosen ciphertext adversary who is an adversary that can choose a ciphertext, in our case an anonymized record, and get the corresponding plain text, that is the original record in our case. Then let's define what I call a maximum knowledge intruder, the worst case intruder. This would be an intruder if we are in a non-interactive setting, like the one we have when creating public use data sets. Known plaintext is the strongest possible attack because the ciphertext, chosen ciphertext, chosen clear text are attacks that apply in the interactive setting. So we take the worst known plaintext case and we assume that the intruder first knows the entire original data set and the entire masked data set, and the only thing the intruder wants to find is the mapping between the records in the original data set and the records in the anonymized data set. So this would be an intruder that is has the largest possible background knowledge, because he knows the original data set, and that is purely malicious. So he has nothing to gain from the attack in terms of information, except tarnish the reputation, discredit the reputation of the data protector. That would be the type of intruder we consider. There are differences between intruders in cryptography and intruders in anonymization, for the simple reason that in cryptography there is one or few legitimate receivers and everyone else is deemed to be an intruder. Okay? So you need to provide utility only for the legitimate receivers. And in anonymization, it's the other way around. So there is only one or few intruders, and everyone else is deemed a user. So you have to provide utility for a lot of people who are not necessarily trusted. So that makes the thing a little bit more difficult. Okay. Now, let's assume such a maximum knowledge intruder, and let's try to see what kind of record linkages this intruder could mount in order to gain some knowledge. Well, this powerful intruder, in particular, can do reverse mapping, the procedure I outlined in the beginning, and obtain the permuted dataset Z corresponding to the anonymized dataset Y. So for him, basically, any anonymization is a permutation because he can get this permuted dataset out of the anonymized dataset and the original dataset because he knows it. Okay? Then he can link any original record in the original dataset to at least one record computed the way he prefers. And here you can use all methods that Peter Christen was mentioning or beyond. A simple method to determine the anonymized record corresponding to an original record X is the one at minimum permutation distance. In this case, we would take distance 0 and to begin with, and then we would say that while there is no record in this permuted data set such that the rank differences for all attributes between values in this record and values in the original record are below or at most D, then increase the distance. And when you find one such record, then you say this record is the one that corresponds to the original record. This is a simple way to do the thing. There are probably many better ways. Now, there is a thing that normally happens, and it is that data protectors often dismiss record linkages by intruders on the grounds that the intruder cannot verify whether the record linkages are correct. And this is called plausible deniability. And this is a great excuse to just forget about intruders linking records. Here we show that our maximum knowledge intruder can demonstrate or can get a good evidence that the linkage did not occur by chance alone. So that makes a difference with usual intruder. If you assume that an intruder knows as much as this intruder, then the linkages he makes are, to a great extent, verifiable. How can an intruder verify whether a record linkage is just random or has something in it? Well, one possible way for intruder to proceed is this way here. The intruder generates a large random set T of values by drawing from the original data set X. T can be viewed as a dictionary, in the extreme case, as containing all records that can be obtained by combining values of all attributes in the original data set. This is a sort of huge data file. If you cannot afford building such a big dictionary because the data set is already very big, then you can take a subset of all the possible combinations of values. Now, the intruder determines the permutation distances at which matches occur between records in this dictionary and records in the permuted anonymized data set. Now, if the distribution of the permutation distances for matches between T and Z overlaps with the distribution of distances for matches between X and Z, then the intruder's matches are plausibly random and he cannot claim them. So if you match the dictionary against the anonymized dataset Z, then you match the original dataset against the anonymized dataset Z. And for each match, you compute what is the permutation distance. And then you draw the distributions of both sets of permutation distances. If both distributions are largely overlapping, then the matches you get from X could have been random, because you can get a similar distribution of distances when starting not from X, but from a random data set, from a dictionary. Okay? Let's use this idea to evaluate several simple anonymization methods. To begin with, we must say that any deterministic masking method must be discarded at this stage, because our maximum knowledge intruder can exactly reconstruct the anonymization process from the original data set. Since he knows the original data set, if there is no randomization, then he can exactly compute the anonymized data set, and he can map each record in the original data set to the anonymized data set. So let's forget about methods that are deterministic with this type of intruder. Now, so deterministic methods out with this type of intruder, at least. Now, let's consider, for example, some randomized method, additive noise, which is a simple one, in the silliest possible way, of course. I apologize. Here we take a data set with 40 records with 4 attributes, and we anonymize this data set by just adding a normal noise with mean 0 and with variance 1% of the variance of the original attributes, okay? Which is very little, by the way. So you can imagine this will not work well, so that's the thing. Then you compute this dictionary from the original data set, the T, and then you compute linkages from the original data set into the anonymized data set Z, and from the dictionary into the anonymized data set Z. And the distributions turn out to be quite different. And then, therefore, this is the result. So here, this distribution for the distances of the linkages from the original data set and from the dictionary data set. So when you get these two distributions, any linkage that the intruder gets from the original data set is not plausibly random. And that's one conclusion. So in this case, the protector needs to increase the noise until both distributions are more similar or overlap more. If you increase the variance of the noise, you will see that this distribution gets flatter and overlaps more with this distribution here. So then, which is the normal thing to expect? More noise and more safety in this case. Now, if you consider, for example, multiplicative noise, also very simple, you multiply the original values by a random value drawn from a uniform distribution between 0.95 and 1.05. Of course, this is a very small range. You can imagine things will not go well. In this case, again, you compute the distributions when matching from the original data set and from the dictionary data set, and you get this here. There is more overlap than in the case of additive noise, but still not enough. The distributions are quite different. So matches from the original data set are not plausibly deniable as being random. Okay, so the protector needs to increase again the noise until both distributions are more similar, overlap more. Rank swapping. Let's consider rank swapping with a parameter 15%. That is, the idea here is that for each attribute, the values of records that are within a rank of 6, that is 15% of the overall number of records, are swapped randomly. And again, we compute the distributions of permutation distances between matches from the original and from the dictionary data set. And you get this. So there are substantial differences between distributions. So again, linkage from the original data set is not plausibly random. You need more swapping or something else. Probably something else. Then let's consider synthetic data, also very simple. I'm ashamed to present this kind of silly thing in front of Jerry, but yeah. The idea here is to sample from a multivariate normal distribution with mean vector, the mean vector of the original data set, and covariance, the covariance of X. And then again, you compute the distributions, and the thing is good enough to pass the test. If you, the linkages from the original data set, given this high overlap, can be claimed to be plausibly random. Okay? So from that point of view, this synthetic method would be good enough for the linkages to be discarded as random. This kind of procedure to compare distributions allows tuning anonymization by the data protector. So you can do things in a way custom. You can customize the anonymization. You don't need to go for a very good privacy model from the beginning. You don't need to go for the utility first approach to see what happens. Well, at least you can do this. This provides some systematic way to calibrate your parameters. Okay. So the distribution of the record level permutation distance for records in the original data set depends only on the level of anonymization. You can expect that the distance, the permutation distance for random records grows with the number of records in the data set and also with the number of attributes. And it is independent of the anonymization level used, okay? Because the random data set contains of all possible permutations of original records and does not depend on the anonymization used, okay? It is something built by exhaustive combination in a way. This kind of verification can also be used by the data subject to verify how good anonymization was. Because before I have shown how the user, how the subject can check the permutation distance. But is that permutation distance that he obtains good enough or not? Of course, if I'm the subject, I find that the permutation distance of my record is D, then I don't know whether D is enough or not. So the good thing is to provide the subject with some way to check whether this D is safe or protective enough. Then the subject can do this. He can use, in the case that anonymization is only permutation without any noise addition, the subject has her own record, and she can not only find D for her record, but also verify whether D is safe. If anonymization involves noise addition, then it's not so easy. Okay? In the case that there is only permutation, the subject generates again the dictionary data set, which she can do from the anonymized data set. Anyone can do. Well, from the anonymized data set Z, which in this case consists of permuting the original values. Okay, we can use the subject can use Z instead of the original data set because one is a permutation of the other. Okay, if there is noise addition, the user has no access to the entire original data set, so this cannot be done. But if anonymization is just permutation, the subject can use Z in place of X and get the dictionary. And then the subject checks whether a match at distance D is plausible as a random match. If yes, D is safe. So for example, in this case, if the distance, here you get a distance, the subject gets a distance 5, well, this is hardly plausible. But there may be regions or some distances in which there is enough overlap. In general, here, any matching distance would be taken between here and here would be considered safe. by a subject. Okay. Finally, almost finally, not yet. We have discussed so far about verifiability by subjects and also by the data protector. Now there is another issue at stake, which is transparency towards the users. Okay? This is another stakeholder here is the user. Well, privacy parameters in general are only explicit under the privacy-first approach. This I call privacy-first approach when using a privacy model, differential privacy or k-anonymity, t-closeness, or the other methods. In that case, there is an explicit choice of the privacy parameter from the beginning, even though the precise method used to attain the model is not necessarily declared. So you say the data are differentially private or are t-closed, but you don't necessarily specify how you manage to satisfy the privacy model. So not all information is available to the user, at least not always. But the worst case is the utility-first approach, which is the one usually employed by statistical agencies and by most people who make a living out of data release. Those people prioritize utility because otherwise they would be shut down, and then they use this utility-first approach, and then they take care of privacy as an afterthought very often. In this case, agencies often withhold the parameters used for anonymization, like the variance of the added noise, the proximity of the swapped values, etc. And this is, of course, problematic because on the one side you have that the users cannot properly evaluate utility. You cannot really compensate for any biases in the data if you are not given the parameters of anonymization. And also, basing protection on parameter secrecy is known to be a poor practice in cryptography. Then why not in anonymization? So this violates the so-called Kerckhoff principle. We can be, at least when considered this maximum knowledge intruder, we can afford being transparent to the data user. If we are transparent, then the user would get all anonymization parameters except the random seeds, okay, if any are used for anonymization. And at least with the maximum knowledge intruder, we must use some randomized methods, otherwise there is no safety. Transparency does not favor our maximum knowledge intruder. It does not give any further advantage to that maximum knowledge intruder because he can compute record linkages and verify them using the previous procedure without any information about the anonymization mechanism. So the user is not given any additional advantage in principle by being transparent, this maximum knowledge intruder. So transparency is to a large extent neutral to the intruder and neutral to the subject, and it is very good to the user. So why not be more transparent? There is an objection here, and it is that, okay, this holds for the maximum knowledge intruder, but normal intruders don't have as much background knowledge. And then I agree that for intruders knowing less, there is a difference between being transparent and not being transparent. That's true. But at least in the maximum knowledge intruder case, transparency is for free. Not in the other case, of course. Imagine that we don't go for anything of what I have been discussing. So we are the controllers. We don't provide any verifiability. We don't provide any transparency. We do things as business as usual, and that's it. Okay, then, and if we are in a big data setting in which no one knows us, we are not ONS, we are not known. No one. We just set up our company some weeks ago, and then we want to do everything in a centralized way. Well, in this case, if subjects cannot verify the level of protection we provide to them, or they can verify it, but they are not satisfied, then the subject may prefer local anonymization. That is to locally anonymize their data and then give the result to the controller, however bad the result may be. Okay. Now, each subject, in this case, would anonymize her own data before handing them over to the data controller, data collector. Local anonymization has quite a good deal of literature already. So you can find things out there. It requires subjects to anonymize their data without seeing data from the other subjects. This is one understandable issue. If you anonymize data locally, you are not aware of the contributions of the other subjects in the data set. So given that permutation is basically, can be viewed at least basically as permutation, it is too bad to be forced to permute without knowing with which, what you are permuting with. Okay, that's the thing. And this is likely to lead to some overkill in the anonymization. So the users just add more noise than necessary just in case. Okay. Therefore, this local anonymization approach normally results in higher information loss than centralized anonymization. So the user can make sure about her privacy, but overall there is less information in the resulting data set. Then there is an alternative to local anonymization that we have called collaborative anonymization, and this is something in the middle. So the idea is to empower each subject to anonymize her own data while preserving utility as in the centralized paradigm. The idea is that the subjects generate the anonymized data set in a distributed and collaborative manner. It's not just me and myself anonymizing my data, but I have some communication with the other subjects in the data set during the anonymization process. We seek here two main properties. One is that information loss must be equivalent to the information loss that would result from the centralized paradigm for the same privacy level. And second, that neither the data collector nor the subjects gain more knowledge about the confidential information of a specific subject than disclosed by the anonymized data set that will be released in the end. Okay? What are the subjects' motivations to participate in a collaborative scheme like this one? Well, first, because this is important, once you ask people to do something, you must make sure they have the proper incentives. Okay? A rational subject should only contribute to a data set if the benefit she gets from participating compensates her privacy loss. I mean, if you think the data set will allow better planning and you are interested in better planning in your neighborhood, then you will contribute. Otherwise, maybe not. A subject without any interest in the collected data is better off by declining to contribute. A subject without privacy concerns can directly supply her data without any anonymization requirements. It only takes the subject some work, but maybe the work is for free. Finally, a subject who is interested in the collected data but has privacy concerns, which is the most common situation, should prefer the collaborative approach, the one we are preaching, because it outperforms the centralized approach by offering also privacy versus the data collector, and it outperforms the local approach in that it yields less information loss. This idea of common benefit is what we have coined. Well, we have coined this notion of co-utility in many settings, but also in collaborative anonymization, to denote cases in which the best strategy to attain one's goal is to help others in attaining theirs. And if a protocol, if an algorithm, is a procedure, is co-util, well, it works smoothly without external enforcing mechanisms. In microdata anonymization, the privacy protection obtained by a subject affects the privacy protection that others get. I mean, if everyone else in the data set sees her privacy disclosed, violated, then you are not very private anymore. So it's in your interest that other people also stay private. Okay? So in this respect, privacy is a common good, as I think public good, I think the economists say. It lends itself to co-util protocols that are self-enforcing in a way. Well, we are doing some research under this Templeton Foundation grant on co-utility in several areas, not only data protection. And let's just briefly mention how you could achieve the k-anonymity privacy model in a collaborative way. In k-anonymity, you have, and this is one of the big problems of k-anonymity, you distinguish between quasi-identifier attributes and confidential attributes, and you assume them to be disjoint. So you have attributes that can be used to re-identify, like age or height or weight. And then you have confidential attributes like salary or blood pressure that are not obviously quasi-identifying, but that are confidential. Now, if we assume that the quasi-identifier attributes are not confidential, k-anonymity is a thing that works, and then the probability of correctly identifying a record in a k-anonymous data set is upper bounded by 1 over k. So what you do is to confuse each individual in a group of at least k individuals. K-anonymity usually assumes that an attribute, as I said before, is either quasi-identifier or confidential, but not both. Then how could we achieve k-anonymity in a collaborative way? Well, very simple. First, in the first stage of the protocol, all subjects share their quasi-identifying, the values of their quasi-identifying attributes. Okay? These attributes in themselves are not confidential, so you can publicly share them with the data collector and with each other. Okay? So, with the set of quasi-identifier values, the data controller can build the k-anonymous classes, the groups, the k-anonymous groups, by just clustering those values and taking the average value within each cluster, etc. There are several ways to do that. And then in a second stage, once the classes have been computed by the data collector and have been published, then you use an anonymous channel like Tor. You send your confidential attribute values anonymously, in the sense that you use an anonymous channel that cannot be traced back to you, to send your confidential attribute values and the identifier of the k-anonymous class. So you say, I am someone, I am not telling you who I am, my confidential attribute values are this, this, and this, and my values must be placed in the second k-anonymous class, or in the third, depending on what my quasi-identifiers are. And as a result, the data controller can obtain a k-anonymous data set with the classes that have been computed in the first stage and with the confidential values that have been added in the second stage. Okay? And you get a data set exactly as you had done everything in a centralized way, so you don't lose any information, and each subject is in control. So if you don't like the k parameter that has been used by the data controller, you don't provide, in the second stage, you don't provide your confidential data. So you want higher k, for example. You have the last word, in a way. Conclusions already. So we have presented a new permutation model for anonymization. We have used this model to show how subjects and also intruders can verify anonymization. We have defined also a maximum knowledge intruder and shown how such an intruder can verify the plausibility of record linkages. And we have applied this to evaluating several anonymization methods. We have made the case for being transparent towards users in anonymization, at least when the intruder is as knowledgeable as this one. And we have explored alternatives to centralized anonymization for the case in which the subject is not happy or does not, with the anonymization, or does not trust the controller, which will be happening more and more often in the current setting. And yeah, so these are the references. That's it. Thank you.
Thank you very much. Questions, comments from anyone? And Sophie.
Did I miss it, or did you not show how your second method said the first method performed? Right, like, so the second part of the talk, you were showing how different anonymization methods perform, and the best one seemed to be the synthetic data approach.
The very silly synthetic data.
Right, but did you try, maybe I got confused the names, but did you try the first method? The one that you proposed, the, I don't know, the permutation?
No, in fact, permutation model is not a method. This is a model that shows that any method can be essentially viewed as permutation plus noise, but it is not a method in itself.
Okay.
It is a construction so that you see that everything basically is is permutation, because you can rank original.
You have a slide at first that was describing it as a method. Maybe I just got confused.
Swapping is a case of just permutation. But any other method, for the simple reason that you can always take the original data set, ranked attributes. You can always take the anonymized data set, ranked attributes. Even if the data are non-numerical, you can even rank them. There are techniques from artificial intelligence that rank anything, at least anything that is even purely categorical attributes. As long as you can put them in an ontology, in a hierarchy, you can rank them. So, and then you can do that procedure of that reverse mapping thing for any method, and that's what allows you to speak in those terms.
So you wouldn't start with a DJ, right? Like, so you wouldn't start and say, I want to change my data and anonymize it such that I get this and this value, but you would apply the anonymization method, and then you can sort of check
exactly whether an intruder can claim that linkages are good or not. And you, as a data protector, should make sure the intruder cannot claim good record linkages. And that's the thing, yeah. I think there was maybe Harvey, you were asking?
Harvey?
Well, I think you just said that. I was going to ask about categorical data. So if you've got something like sex, you can rank it, but you essentially you've got all those ties there. Yeah. And I wonder how the statistics you described perform when you've got lots and lots of tied ranks.
Yeah, when you have ties, you randomly assign ranks within the tie. That's true. I mean, if you have microaggregation, which is a method I'm quite fond of, you replace a set of values by an average, then you have ties. In that case, you need to randomly undo the tie. Of course, it's not a brilliant thing, but it is a way. I mean, the argument still holds that you can view everything as a permutation. But of course, in that case, you must undo the ties in a random way.
I mean, one way around that, one way of mitigating that is to look at combinations. I mean, you're dealing with each variable in turn. If you have several categorical variables, you look at all the combinations, and then you will have less ties.
Yes, that's true. But what I wanted to convey is more the view of anonymization as permutation plus small noise, more than the view holds. Then it may be easier to apply or less, depending on. For numerical data, it's very easy, as long as you don't have ties. For categorical data, it takes some more work, but in the end, it can be done. So the functional equivalence holds. That's the thing. Yes.
So some of the things you said, from perspective of the agencies, sort of makes sense. Like when you were talking about anonymize your data before you submit it.
Yeah.
That happens all the time because people make a lot of, they give messy data.
Yeah.
They don't give you their exact income.
I do that. I do that.
So, and then the issue of the, what did you call it, collaborative anonymization, and I think that's sort of similar to this sort of randomization method. Give us a true answer with the probability of p, that sort of thing.
Well, it is
related to the post-randomization.
Local anonymization is randomization. That's randomized response in a way is local anonymization, in which you do things on your own without knowing anything about the others. The difference with collaborative is that you know something. For example, in this case of the collaborative k-anonymity, you first see the listing of all k-anonymous classes, and that means something. So when you give your data in the end, you have knowledge about the other people, some knowledge. Then finding collaborative algorithms or methods or protocols for other privacy models is what we are at the moment trying to do. I must say also that you can play tricks here. Imagine that the data controller wants to frame you, and you are the only one in your class. He invents fake subjects who don't exist, and you are the only one that is authentic. That's a way to frame you. Then we are now trying to find, and we have found some solutions for this problem. They involve some cryptography, some cases. Well, I mean, this is the basic thing, but then you can, if the data controller is not only honest but curious, but is also malicious, then the thing is bad. For an honest but curious data controller, this works. For a malicious data controller, you need more. Yeah. But so far, I think no one assumes that controllers are malicious, so far. If we start assuming this, it's the end at the moment, yeah. But honest but curious, they can be.
You're giving them the idea now.
Yeah.
Any other questions or comments on the talk?
You spoke so fast. There's so many new things you were throwing at us.
Well, because this is the...
Absorb this. This is all completely new. And,
Well, I think this is what we were supposed to do.
absolutely.
Well, I mean, there are several... When you think of big data privacy, which is something I'm in these times thinking about, there are several problems. So you have this volume, which calls for fast algorithms for anonymization. You have this velocity, which calls for dynamicity, algorithms that can deal with changing data, with streaming data. And you have diversity, which calls for linkability, for allowing some linkability between anonymized data sources. But you also have the requirement to empower the user, the subject, because people are helpless in a maze of people collecting data on them, and then you must be given some tools to defend yourself.
So is there some motive, like in the has there been some subjects saying, I want to know how anonymized my data is? This is a real problem, you think?
I think that now that everyone has a smartphone or something which is a personal device, you could make a good use of collaborative or even local anonymization methods. You don't need to know about them.
No, but the fact that you're giving the subject, the person, tools to be able to say how anonymized is my data.
I mean, there is something that I don't know whether there are any Germans around. Yeah, they are. Yeah, I don't know. Yeah. Okay. Yeah, so there is something called self-determination, Selbstbestimmung. I think that was invented long ago by the Constitutional Court.
Complicated. It's called informationelle Selbstbestimmung.
Okay, yeah. So, and then there is an increasing trend to move from privacy understood as seclusion or just keeping my data to myself to self-determination. So as long as you are able, as long as you are in control of your data, it's okay. But at the moment, in the centralized model, no one is in control of their data. Either you give them or not. But there is no way in which you can control anything. And this is a call for providing people with tools to control.
So part of the work, I guess we're presenting tomorrow with Harvey, is the fact that so as statisticians, we're worried about measurement error and all the problems that this anonymization procedures cause, and of course we need the parameters. So the noise parameters. So what is the argument? So here you're saying yes, we should be releasing the parameters, but how do you convince agencies to do that? And I think this is a real.
I mean, this relates to the other section on transparency. I say when I consider such a powerful intruder, transparency does not give the intruder any further advantage because the intruder already has a lot of advantage. But it's true that when the intruder doesn't know so much, it makes a difference to give the intruder the parameters or not. And that's where the thing...
So is there anybody doing research on this sort of, how disclosive are these parameters?
Alan Carr and Larry Cox used to wrote a good paper on that, I think on statistics, I don't remember the journal now. Maybe you are...
No, sorry, I'm going on a different thought pattern because also if you're doing the local anonymization, then what are the parameters? How do you actually get them at all?
No,
don't release them.
There are local anonymization methods, for example, that provide differential privacy or k-anonymity. So you are told behave in this way exactly, and if you do exactly this, the result will be an overall data set that will be differentially private with this parameter, or that will be k-anonymous in this parameter. But then the question is whether people exactly do what they are told. You have no guarantee. Because it is in your interest to overdo, just in case.
You can give them the machine.
Yes, if you can give them the program, but...
And say, well, I'm satisfied with that or not. I don't send
yes.
it until I'm not satisfied decide.
But if you really give control to people, they may decide not to follow the prescribed.
I mean, if you give them the technology, they just push.
Yeah, but then you are not giving control to people. You are just giving them a program.
They are happy with what the output they send it. Otherwise, they push.
But they will have no criteria to decide whether the output is good or not.
Yeah, and then you have bias, of course, for the people who don't.
So in theory, you can achieve privacy models in a local way, but if everyone follows the rules, which is not clear. So.
Any other questions, comments? Okay. Well, thank you, Josep, again.